Hello again. Glad you're still with me. Over the last few videos, we've been unwinding the concepts of energy and work and showing how they're related. And we've seen power. We've seen, finally, in the end, the full 3D version of motion. And we've also seen, in a few examples, how we can use these ideas along with the work energy theorem to solve some basic problems, namely identify a system, focus on the interactions, and figure out how much the energy, in this case kinetic energy, changes on the inside of the system. And that is related to the work done. In this video, I'm going to take a closer look at the formula we had for work, and that's going to enlarge our concept of energy. Thus far, we've only really had kinetic energy in our systems. Today, we're going to enlarge that to incorporate potential energy. We've actually already seen it. It's just, I didn't draw your attention to it. You know, have to walk before you can run. So potential energy is going to be a new form of energy. That's how we're going to think of it. And it's going to be associated, there's a lot of words here. So, okay, it's going to be associated with an energy that you can think of it as some type of energy such that you can place, so energy can go into potential energy. So maybe kinetic energy can be converted into potential energy. And if it's a potential energy, then at a later time, it could be returned to your system. So you can think of it as, breakfast. There's, the sun shines light on the grass, blah, 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 lots of chemistry. I don't care. Goes to the factory. They produce Raisin Bran, whatever. And so then that's got energy. It's stored in your cereal. And then your body consumes it and then can be turned into kinetic energy. So if you want, it started as kinetic energy of sunlight, whatever that means. And then it gets converted to potential energy in the form of breakfast. And then it's returned to kinetic energy in the form of your motion. So that's kind of the idea. It's a type of energy that you can think of the system as having at any one time. You could have high amounts of potential energy or low amounts of potential energy. And as the potential energy goes up and down, then you have more or less potential for motion. That would be one way to define it. It turns out that potential energy forms are intimately connected with types of forces. And not just any force can be connected to a potential energy. It's only forces which are said to be conservative forces. And I'm not talking about politics, I'm talking about, there's something special in the structural mathematical form of the forces. So I want to unwind that and we'll get to kind of see how that works. Okay, so key ideas with potential energy is a form of energy that you can kind of set the energy there. You think of it almost like, it's like a shelf in the kitchen, right? You have food and then you can kind of set it up on a shelf. It's fine, you can sit there for a while, and then at a later time you can get that food back. Okay, so that's kind of how I think of it. Okay, so we're going to have potential energy is a type of energy that can be stored, and that's going to mean that, well, let's think about what that would mean. Because potential energy is, we think of it as an energy which labels the system. So imagine now I have a system And now I have both kinetic energy and potential energy. Okay, both kinetic and potential energy in my system. And I imagine that I can somehow exchange these back and forth. They're fungible. You can swap them out. So, well, we've seen kinetic energy already as an energy in terms of how it's related to forces and things. So there has to be some connection between potential energy and work. On the other hand, I'm thinking of this as a state variable. At any moment, in any situation, the amount of kinetic and the amount of potential energy characterizes the condition of the system. So it's a little different also than work. Because when you think about work, let's break that apart actually. When we think about work in general, to evaluate work, let's say in 1D, you have to integrate the force over the distance. So that means that it depends upon all the details all the way from the beginning to the end of the path. And in general, it actually depends upon the path. So if you go to 3D, and for those of you who've had Calc 3, you should know this already. You are. Okay. In general, when you evaluate this work integral, you just have to take it on faith if you haven't had Calc 3, but the way that you wander through space affects the answer that you get. And you have to kind of evaluate this little dot product along each little differential baby step. And the way that things line up or don't line up, it matters. So in general, this depends upon the path. But if the work depends upon the path, then it can't really depend upon, it's hard to think of it as being associated with labeling the state of a system, or more precisely, changes in the state of a system. So there has to be something special. So there has to be some special condition, or specifically, some special kind of force which allows you to associate the work of that force in some way with something called a potential energy. The key insight I've written up here, and what I have there is a fact. We've seen it a couple times now, either with time derivatives or spatial derivatives. It doesn't matter, but it states that the integral of a total derivative depends only upon the difference in the function. And that's actually true in all dimensions, in 3D as well. So you have to work out what is a total derivative. It's related to something called a gradient. But what happens is that if the integrand just happens to be a total derivative of a function, then when you integrate it, it just evaluates to the upper limit minus the lower limit. And you can think of it as the work being numerically equal to the difference of a function evaluated at the beginning of the process minus the end of the process. Specifically, you can associate it with a potential energy. So there's a special situation if, and only if, the force, and I'm working in one dimension, there's a generalization of this to 3D, but that involves vector calculus, so I don't want to get into that. But the concept is the same. If a force is associated with a derivative on a scalar function. So we would say, and you actually put in a minus sign there. Okay? So we say if, and only if, the force is a total derivative of a function. The function is going to be called potential energy when we're done. So U is going to be the potential energy. Then look what happens. The work in going from initial to final equals the integral from x initial to x final of f dx, which equals minus, the minus sign is really there for convention. If you've had chemistry, you know, you've talked about potential energy there, and you know that we typically want the ground state to be stable. So we want there to be typically a lowest possible energy level. It doesn't have to be positive, but there has to be a bottom, okay? And this minus sign is associated with that. Anyway, completing the story, the integral of d by dx on u dx. Okay, so all I've done is said if the force has this form. They don't all have that form. Friction does not have that form, for example. Then you can plug it in like this, and the work integral is the same as the integral of a total derivative. That means I can associate the work with a minus sign times the change in U. All right. Forces that are like this are said to be conservative forces. Conservative forces are only related to total derivatives of a function, and it has to be a scalar function, actually. Remember I said, so you can think about potential energies as storing energy. And what that means is that if you put energy into potential energy form, it can always come back. And the way you can see that in this language is if this is an integral and you integrate it forwards and you turn right around and reverse the integral, then look what had happened. Since the integral is going to be a total derivative, you're just going to get delta U going forward plus delta U coming back, and you're going to find no change in potential energy. So what that says is that basically you start with some potential energy. If you add more to it, and then you take that added amount back, you get back to where you started. So going around a closed path in the space of states doesn't change the potential energy. So if you start with an amount of potential energy, you do whatever, blah, 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 you come back to the same state, the same condition, the amount of potential energy will not change. That means it also is a state variable. It characterizes the condition of your system. Okay, so that's kind of a mathematical way to say all this. Remember this minus derivative thing. Minus derivative is going to come up in some of the examples we do. Okay, so now generally when we want to talk about a system and talk about all the types of energy, we kind of have a little bit of everything. So I think what will be easy is if I give you some examples of forces that are total derivatives, and then we can use them in some examples. And the most important example for us will be gravity. Again, physics 1, everything's about gravity. So let's look at the force of gravity, the weight. The weight is minus mg in the y direction. I'm just going to work with the magnitude here. because we're going to focus on 1D motion. I said magnitude. That's not magnitude, but it's just 1D motion focusing on. Okay, so the force of gravity is minus mg. And I want to ask, can I think of a function whose derivative in that direction gives me weight? And the answer is, you can imagine a potential energy, U, which equals mg times the height, y. So U equals mg times the height, y. I apologize. I keep getting into this shit, this glare. U equals mg times y, the height, y. Sometimes people say mgh, but we've used y as a coordinate for up and down through most of the semester. I feel like I should stick to that. So that's what I will do. mgy. Now, mgy is a perfectly adequate formula, but you have to say where you're measuring. What do you mean by y? So usually we mean the floor to be 0. So this is fine. This would say that the potential energy when y was 0 was 0. It's a fine choice. It's a convenient choice. Almost always it's the best choice for our kind of problems. In fact, though, the only thing that really matters is that the weight have the same form. So let me go ahead and write this over here. The force is related to a potential energy by minus a derivative. I'll say x. It really would be along whatever direction the force acts. Okay? So that's kind of our master formula. And we notice using this master formula, you can always add a constant to U. You can add a constant to the potential energy, and it does not change the force. We see and measure force. We don't so obviously see and measure energy. We usually measure it in indirect ways. And so there is no way to pin down the exact value of U as long as it has the right slope. So you can always add a constant to that. It's how you can set the 0 point of energy. In chemistry, one of the ways you typically do it is in chemistry you say that the energy of a fully ionized, just barely ionized atom, the energy of that is 0. And you measure all energies relative to that by convention. It's not physical, it's just a choice. By saying that the potential energy is 0 on the floor, that's a choice. Nobody forces us to do it. We just made that choice. So in fact, we can actually use that freedom to write a more general expression for potential energy and say that potential energy equals, I think I want to change from green. It doesn't seem to work very well. Potential energy equals mg times, and I can add a constant, and I can define, and I'll call this y minus yr for reference. Yr is a place where we choose U to equal 0. So what's happening here is the value of energy actually doesn't matter for nature. The value does not matter, but the value does not matter, but differences in U do matter. So as long as we look at potential energy differences, adding a constant doesn't change anything, and we can choose this constant to make potential energy a convenient value or formula. If you've ever done any circuitry or you know anything about that, this is exactly the same idea as saying that something is grounded. When you say that something is grounded, you're basically declaring it to have zero potential energy. It's not. It's okay. And we typically choose that to be the ground, okay? But you wouldn't have to. You could choose anything that was convenient. So it's the same concept. All right, so this is our formula for potential energy due to gravity. It's connected to our formula for the weight, which is minus mg. All right, so let's see how this plays out then. We can imagine that we have an object that falls, like a ball, okay? Or a marker that falls. And we can choose how we want to describe this. We can either say that my system is only the ball. That's fine. But if I make the system be only the ball and nothing else, then I have to view gravity as something, because that has to do with the interaction between the ball and the earth. So I have to think about gravity as a work being done on the ball, causing it to speed up as it falls. Or we can choose to include gravity in the system, in which case we don't think about the work due to gravity. We think about the potential energy of gravity that's stored in the system. So the idea would be you make the system be the earth plus the ball plus their internal interactions. And then you would have a kinetic energy for the earth. We'll assume that that doesn't change much, so it just never appears in the formulas, but it should be there in principle. And then you have a kinetic energy of the ball, which does change significantly. And finally, you have a potential energy change due to the interaction of gravity. So if we define the system to be ball and earth, then in my system, I have both kinetic and potential energies because I'm including the earth in my system in that case. And then the interactions between them have to be handled with potential energy. So I would have kinetic energy and I would have potential energy. Now, you still could have work done with the rest of the environment. So for example, if you had drag force is not going to be a conservative force. Friction is not a conservative force. If you have friction or drag, you have to handle them using work. But if the forces are nice, then you can describe things with a potential energy, and that is almost always going to be preferable it's going to be preferable to use a potential energy rather than the work formula. So let's see how this works. I want to set up my work energy theorem now as change in kinetic energy plus the change in potential energy, call that delta U, equals the work done on my system. On the other hand, well, you can kind of see what's happened here. On the other hand, I had that the work due to a conservative force was minus delta U. So what actually happens is as follows. If you think of gravity as being inside the system, then you have a potential energy. and it appears grouped with a plus sign and is next to kinetic energy. If, on the other hand, you choose to make the system be the ball alone and gravity is outside the system, then this term has to be grouped over here with work, and you pick up a minus sign. And that's why when we define work to be, for conservative force to be minus delta U, that it had a minus sign, right? So it's really an issue of when you do the bookkeeping, do you put the energy, this form of energy over here as like a state variable, part of the system, or do you rework it over here with work and view it as an external thing? It's the same ball, it's the same earth, and it falls in the same way. How you treat this is really a matter of choice. I will tell you, if you can use potential energy, it's much easier to put all of the conservative forces that you can in potential energy form rather than evaluating a lot of integrals. Okay, so if you know the formulas for potential energy, it allows you to basically bypass having to do some of these integrals to calculate work, especially when the forces are not constant. For constant forces, it really doesn't matter. But for non-constant forces, it's just tedious to always have to do the integrals, whereas if you use potential energy, it's just done for you. Okay, that's what potential energy is. I'm going to do some examples in the next video.